Uh, I mentioned on Monday the path and the parent model. Let's say that R is the interest rate or growth rate. Because it's interest rate, well, in this case it would be growth. In other words, this is the interest rate when you deposit something rather than borrow something. Okay? And the model will be P of t equals P sub 0, 1 plus R raised to the power of t. Okay? What we'll do, we're going to say that, actually, let me use the whiteout here. I want to change the name. I want to use R as the growth rate and interest in parentheses. And you'll see in a minute why I want to use this terminology. Okay, let's hope that this is dry enough. So R is the growth rate and I'm going to underline the word rate. In this case, we are talking about compound interest, so it would be the interest rate. Okay. Now the quantity 1 plus R, we're going to let A equals 1 plus R, and we're going to call A as the growth rate, the growth factor. Sorry. And I'll underline the word factor. Okay, so we have growth rate and we have growth factor, and they are related to each other in this manner. A, the growth factor, is 1 plus R, and therefore now the path model becomes, so if we let A equals 1 plus R, then now we have the model P of t equals P sub 0 A to the power of t. Okay, and this is the path model. The path model serves well when you're dealing with annual percent rate or annual rate. Are you downloading something on the computer? Because I hear that sound. All right, so this is the path model. Let me underline this as well. Now, let A equal e to the power of R. Okay? We can always express any number as an exponent with natural base. So now, instead of the path model that we see here, after the substitution, then we have P of t equals P sub 0 e to the R raised to the power of t, right? And of course we know that if we multiply it out, we get the parent model. So what it means, if we let A equals e to the R or vice versa, then the path becomes the parent model. Okay. So we're going to write a note here, or comment. P of t equals P sub 0 A to the power of t, refers to an annually compounded interest. Oops. On the other hand, the PERT model refers to continuously compounded interest. And hopefully in your pre-calculus and algebra day, you learn how to transition from one model to another. But when you come to natural phenomena such as radiation, or for instance growth of bacteria, chemical reactions, the effect of enzyme, absorption of medication in the bloodstream and so on. Naturally, we're going to use the continuous compounding. It's not interest in this case, but rate, because these changes happen continuously. When it comes to finance, those things are usually done periodically or annually. We usually pay loans, car payments, we make payments either monthly, or if we buy a car, they buy here, pay here outfit, then we pay by paycheck or bi-weekly, stuff like that. So those will be either, if it's annually, it will be the PAT model. If it's periodically, that will be the next model. So here we're going to talk about interest compounded periodically. The model here, we're going to say that R still going to be our annual interest rate. I'll use the Latin term per annum. I think there are two N's in per annum. This is also known as APR, annual percent rate. And let's say N is the number of periods in 1 year if the rate is per annum. So in this case, the model is going to be something like that. Let's see. Let me write it at the bottom here, because I hate to change sides. P of t equal P sub 0, and instead of 1 plus r, since we are compounding n times every year, the rate will be divided by r, by n. The rate r will be divided by n, but on the exponent we have, instead of just t, we'll have n t. Like so. For instance, if we compound it monthly, then at 8%, R will be 0.08 and N will be 12. Right? So the title will be Interest Compounded Continuously. Or, interest compounded continuously. And what I'm doing next is really giving you the proof of the PERT model. You see the comment here underneath the say the PAT refers to annually compounded interest and the PERT refer to continuously compounded interest. And I just made a statement here without showing you why. Here comes the why or the proof of that. Okay? We're going to start with, if we compound it continuously, then if I'm looking at the model right here, then for continuous model, P of t will be the limit as n goes to infinity, because what does it mean continuously? It means that for the period in 1 year, we're going to compound it infinitely many times. We'll have infinitely many periods. So it will be the limit of what I wrote below here. And what I wrote below is P sub 0 times 1 plus r over n raised to the power of nt, like so. Right? And now I'm going to work on this limit and see what comes out after that. So it involves a little bit of trickeration here. Trickery, I should say. Well, trickeration is one of the sportcasters on ESPN like to say. So what I'll do, I'll look at the exponent and multiply divided by r. So everything else I'll keep the same. So I'll have P sub 0 times 1 plus r over n raised to the power of nt, and then I'll multiply and divide by r, like so. Okay? Now, I'm going to rearrange the exponent and say this will be the limit as n goes to infinity of P sub 0 1 plus r over n still, but now I'll do the following. I'll do n over r, which is the reciprocal of r over n, and what's left is rt, like so. Okay, so it's the same value. It's still, if you reduce r with r, you end up having nt, but now I have the n over r component that I'm shooting for. All right? Now I'm going to do a little variable substitution. I'm going to say let x equals n over r, and therefore r over n, which I have in the base, will be 1 over x. Okay? So we perform these two substitutions, and at this point P of t will be the limit as n goes to infinity. And let's see what we have. We have P sub 0 times 1 plus r over n, but r over n is 1 over x. Right? And then we have n over r, which is x, rt. So I write it as x times rt, like so, on purpose. Okay. And remember the property of exponent. If you have a product in the exponent, it's the exponent raised to another exponent, right? So the next thing I'm going to do, sorry. I'm sorry, I'm in the middle of class. I shouldn't have taken your call. Just tell me who you are and I'll call you back. I'll call you back as soon as my class is over. Bye-bye. Sorry about that, but medical related call that I forgot to turn off my cell phone. That's the story, really. Okay, so let's go back, and I'm really ashamed. Huh? Because we tell the student not to do it, and I just did it. Okay, here we go. So it will be this one and raised to the power of RT. Because it came at the poor time, because this is almost a clincher here. So, do you recognize the quantity in the bracket?
Yeah, it's like pre-path.
So basically, you tell me that you don't recognize it.
I thought I did. I was thinking, because just before we went to the path, we got initial P times 1 plus R to the power of T. And then I used to go, well, it's FCR for 1 over X and T for X. I go, that's pretty fun.
The answer, my friend,
Is that wrong?
is blowing in the wind. But this is it. Do you recognize the third definition of the number E? The limit as z goes to infinity, or x goes to infinity, of 1 plus 1 over x raised to the power of x.
That's why you can't continuously.
What do you have here? This is E by definition. That's what I did last time. Because I knew they were going to need it here.
That's why you can't become really near, but continuously compounding forever.
I'm sorry?
Isn't that why you can't continuously make money? Like it has a limit.
I'm not sure that this will be the right application. That's why you cannot continuously make money. There is a limit. That has to do more with logistic equation. This is a different type of exponential growth and decay. But this is strictly what I'm trying to show. I'm trying to prove that if you compound continuously, this model, which we understand, becomes this model. Because the question is, how come we start with something algebraic like this and it becomes exponential with the base, natural base? And this is the proof why this is true, because by definition, this equals to E. So now we include it, and I'm sorry, there is one more step that I should have done. Okay, so let me, again, that telephone call interrupted my train of thought, so let me just make a minor adjustment here. Again, one of the properties of the limit is the limit of a composition. If you recall, we used it also on Monday, last time. The limit of f composition G can be f the limit of G. Remember that? It will be f composition limit of G. And that's what we'll do. We'll take the p sub 0 outside the limit, okay, and we'll take r of t outside the limit as well. And we're going to say here we have the limit as n goes to infinity of 1 plus 1 over x raised to the power of x, and rt will be on the outside. Now, this limit is exactly E, and maybe that's why you guys did not recognize the fact that we have E hidden here. So this by definition is E. So here's the end result. This is the result. This is the proof. So if we compound continuously, then we end up having p sub 0 e to the power of rt as advertised. So in case you ask yourself, when you learn about it in college algebra and pre-calculus, why it is true, all of a sudden how we jump from the path model to the paired model and say, yeah, we're going to apply this whenever we have continuous compounding, here's the proof. But it takes knowledge of basic calculus to understand that. And that's why your teacher, when they taught you that in the past, couldn't show you this procedure. All right, so hopefully you learned something here.